Okay, now picking right back up where we left off, we left off with labeling these different types of atoms for their type of bond, the type of bond that they exist in. So CH, we talked about how hydrogen is a nonmetal, carbon is a nonmetal. Nonmetal and a nonmetal, that would be a covalent bond. But it's not the same nonmetal. So with the information that we have, we would have to assume that this is a polar covalent bond. Now, if it was the case of CH4, well, we've talked about how those hydrogens and carbons, there's some polarity there because there's a difference in electronegativity, but the differences all balance each other out. So this would not be polar, but just one carbon-hydrogen bond by itself would be polar. Magnesium and hydrogen. Hydrogen is a nonmetal. Magnesium is a metal. So nonmetal metal, that tells us ionic. And then Pb and Fe. Pb is lead, and it's below the stair step. So is Fe, iron. So lead and iron mixed together, that is going to be a metallic bond. Okay. Now we're moving on to drawing Lewis structures for the following molecules. So going back to our rules for drawing Lewis structures, the first thing that we're going to do is draw each element with its number of valence electrons. Now, we talked about main group elements, 1 and 2, and then 3, 4, 5, 6, 7, and 8. Now, carbon is in group 4, so it has 1, 2, 3, 4. And then this carbon has 4. And then this hydrogen has 1, hydrogen has 1, 1, 1, 1, 1. So we have 4, 8, 9, 10, 11, 12, 13, 14 valence electrons all together. That's going to tell us how many we need to participate in bonding. So the next step is to put the largest atom in the middle. Hydrogen is only 1 proton, it's very small, so carbon will go in the middle. Let me scoot that over a little bit. We'll put the 2 carbons in the middle, and we know everything has to participate in at least one bond. These are 2 nonmetals, so we know it's covalent, so we're drawing the lines that indicate that we share electrons. And each of these lines counts as 2 electrons, right? It's 2 electrons that are being shared amongst partners. So we've just written 2, 4, 6, 8, 10, 12, 14 electrons. So if we've done this right, we've used up all our valence electrons and everything will be happy. H follows the duet rule. It only wants 2 electrons, so this hydrogen is connected by 2. Hydrogen 2, 2, 2, 2, 2. However, carbon follows the octet rule, so it wants 8 to be happy. So is this carbon surrounded by 8? 2, 4, 6, 8. Yup, sure is. This carbon surrounded by 8, 2, 4, 6, 8. It is also shared by 8. So we have a valid Lewis structure there. Okay. The next one, we have potassium and fluoride. Now, potassium is here, fluoride is here. So we have a nonmetal bonding with a metal bonding with a nonmetal. So we need to draw an ionic bond. So potassium is in group 1. So potassium has 1 valence electron. Fluoride is in group 7. It has 7 valence electrons. So we need to draw it with all of these valence electrons together. So we know potassium, it's a metal, has low ionization energy. It's going to donate its electron to fluorine, which is very electronegative. It likes to attract electrons. And you're going to end up with something like this. A K that has a positive charge because it just lost an electron, and a fluorine, I almost drew chloride, but fluoride that is surrounded by 8 electrons. So it has a stable octet, but a negative charge because it gained 1 electron. And then this would be our valid Lewis structure. All right, let's try bromide. So bromide Br is here. It's in group 7, and there's 2 of them, right? So bromide is a nonmetal. So we know that it's going to be covalently bonded. Okay, we have 2 bromides. They both have 7 valence electrons. So 7 plus 7 gives us 14 total valence electrons. Hey, what a coinky dink, just like methane here. So how will we draw these bonded together? Well, the first thing we need to do is draw our line that connects the 2. And I can kind of see that if I just fill out the outside of both of them, that I'll end up with 8, right? Because I just used up 1 electron and 1 electron. So I have 6 electrons left on either atom. So I have the 6 dots. If I draw 6 dots surrounding this bromide, 6 dots surrounding this bromide, they're sharing the line in the middle, so they each get an electron there, so that they would have 8 altogether. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. They're both happy. They have the correct number of valence electrons. That is a valid Lewis structure. Okay. Moving right along to hydrogen chloride. Now we've worked with this chemical, hydrochloric acid. So hydrogen is a nonmetal. Chloride is also a nonmetal. So that tells us that it's covalent, and we'll be drawing lines and dots instead of just brackets and dots. I'll draw hydrogen, and it has 1 valence electron, and I'll draw chloride with 7 valence electrons. And it's very similar to potassium and fluoride, the only difference being they're nonmetals this time, so we'll draw a bond between the 2. And then, much like bromide, I know that it has 6 valence electrons, so I'll put those 2 dots around. So hydrogen obeys the duet rule, only has 2, and it has 2 in this Lewis structure. And then 2, 4, 6, 8. Chloride is surrounded by 8, so this is a valid Lewis structure. What do I mean by it's a valid Lewis structure? I mean that, first of all, it has the same number of valence electrons that we started with, which is 8. And then second, those 8 electrons are being shared so that every hydrogen has 2 electrons surrounding it, and chloride has 8 electrons surrounding it. Chloride has 8, hydrogen has 2, so it's valid. Okay, H3CCl. That can look a little confusing, but it's totally correct. Hydrogen, nonmetal. Carbon, nonmetal. Chloride, also a nonmetal. So these are all nonmetals, so that tells me that, again, we're dealing with a covalent molecule here. So first thing, write out each of our molecules along with the number of valence electrons it has, right? Carbon, group 4, hydrogen, group 1, chloride, group 7. So carbon has 4, hydrogens each have 1, and chloride has 7. So 7, 8, 9, 10, 11, 12, 13, 14. Again, I swear I didn't do this on purpose, but again, we have 14 valence electrons, okay? So we need to draw our Lewis structure. So carbon is the largest. It goes in the middle. Chloride is the next largest, so it will also go in the middle. And then we need to start arranging these hydrogens. I'm going to start on the carbon because it's the largest. And I've got 3 hydrogens here. Now, let's see how many valence electrons I've used up so far. 2, 4, 6, 8. I've used 8. So now from 14 minus 8, it would give us 6. So now I need to place 6 electrons somewhere. Well, carbon has 8 electrons. Each of these hydrogens has 2. So chloride is the only thing that needs electrons. So I'll give it the 6. Now it has 6 dots and 1 stick. So that's 8 electrons altogether. Carbon, 2, 4, 6, 8 has 8 altogether, and then each of the hydrogens has 2. So that is the valid Lewis structure in that case, which leads us to, last but not least, lithium oxide. Now, lithium is over here, it's a metal. Oxide is over here, non-metal. 1 valence electron and 6 valence electrons. So let's draw that out. Since it's a metal and nonmetal, this will be a ionic bond. Okay, so essentially what will happen is each of these lithiums will donate, can you see that okay? Will donate an electron to oxygen, and you'll end up with 2 lithium atoms with no electrons, which have a 2+ charge, and then oxygen, which has a full octet, which has a 2- charge. Okay. Whew, that was fun. So now let's go on to 26. Draw a visual representation of metallic bonding in silver. So silver is I almost said Hg. No, it's Ag. Silver. So the way that this was drawn in the literature that I gave you is they drew an Ag to show the nucleus of these silver atoms. And then they drew this sort of like craziness happening in between. And this craziness represents the electrons, right? Now, I believe there will actually be a test question that asks you to draw a visual representation of metallic bonding. And I think it's maybe sodium. You can draw this, and that's totally fine, but just show that, like, show a key that shows this is the valence electrons. And then if you want to draw the Ag equals the nucleus. Okay. Remember, metals have a very low ionization energy. So even though they have a strong attraction to electrons, the electrons are sort of free to travel from one atom to another because there's not a lot of energy that's required to make them move from one place to the next. So that's what it should look like. Now we're moving into number 27, which is ranking each of the following bonds 1 to 5 from least polar to most polar. So how do we calculate that? Well, we basically take advantage of the fact that electronegativity increases as you go up and to the right. And we'll say, okay, well, then in that case, what's the difference in electronegativity between these two atoms that are bonded together? So let's start with CH. Carbon, you'll notice, is right here. Hydrogen is over here. Those two are from 1 to 6. There's a pretty substantial difference there. But we don't know where to rank that. So we'll just put it in the middle. Okay. For now, we'll just put a question mark on that one. Let's ask ourselves which of these are the furthest apart. I suspect that it's sodium and chloride. So let's try that. Sodium is over here, and chloride is way over here. That's a huge difference. They're on opposite ends of the periodic table, and you can't get much farther away from than that. So this is going to be most polar, I think. Now, how did I know that? Well, the main criteria I'm using to determine that is I'm measuring the distance between both sides, but also the fact that I know that one is a metal and the other is a non-metal, and then everything else I can automatically tell is a non-metal with the exception of silicon. That tells me that these two are going to be very far apart. So this is the most polar. What's further away after that? Well, C and O. Okay. Silicon and fluoride, Si and F. How far apart are they? They are 1, 2, 3, 4 spaces apart. C and O are only 2 spaces apart. C and H are 1, 2, 3, 4 spaces. Okay, well, since silicon and fluoride are 4 spaces apart, there's going to be a larger difference in electronegativity there. So fluoride is going to be more of an electron hog, in other words, than silicone. So this would be my number 2. Okay. But I'm at kind of a dilemma here because carbon and hydrogen are also in that situation. But the thing is, if anytime you see hydrogen, hydrogen is just 1 proton, so it's not very polarizable. So this one, it's going to be a little bit less polar. Okay, anything with hydrogen is going to be not as polar as something like silicon and fluoride, which has 2 larger atoms. So this one, I'm going to rank as one of the least polar. 5. Wait, is that right? No. This one's only 2 spaces apart, so this one should be 5 because there's not very much of a difference. And then this one would be 4. And that leaves us with NH, which I haven't really talked about yet, but N and H are 1, 2, 3, 4, 5 spaces apart. But again, it's hydrogen, it's not very polarizable. So I'm going to make that a 3. I won't ask you to rank these on the test, just in case you were getting really confused and worried about that. Okay? All right, let's pick it back up on the next video.